Welcome back. In this video, we're going to study rational exponents. And rational exponents are essentially a fractional exponent. So we're going to be writing our exponent as a fraction. So for example, we have a to the m divided by n, that's our fraction, where m is the power and n is the root or the index. So whenever we see a fractional exponent, we need to think power over root. Power over root. Okay, so the numerator of the fraction is the power and the denominator is the root. So the root could be a square root or cube root or fourth root or fifth root, that kind of thing. And there's a couple different ways to evaluate fractional exponents. Well, first we're going to convert it to, a to the m over n. We have our power, so it's a to the m, and our root, so a to the m to the nth root. Where in this case, we would apply the exponent m and then finally take the nth root of it. Or what we can do, we can take the root first, take the nth root of our number, and then apply the exponent m. So these are both equivalent. You can apply the exponent first, then take the root, or you can take the root and then apply the exponent. A lot of this will depend on how difficult the numbers are and how challenging they are. Sometimes it's easier to apply the exponent and then take the root, and sometimes it's easier to take the root and then apply the exponent. So let's take a look at some samples with fractional exponents. So 36 to the 1/2. So we're looking at power over root. So it's 36 to the first power, and it's the square root of that. So we've got the square root of 36 to the first power. Well, this is simply the square root of 36, so our answer is 6. 125 to the 2/3 power. So we've got power divided by root, so the cube root of 125 squared. So we want the cube root of 125 squared. Well, it doesn't make sense for us to square 125 and then take the cube root of that. Really what we want to do here is we'll take the cube root of 125 first, and then we'll square our result, because we know the cube root of 125 is 5, so this turns into 5 squared, or 25. So 125 to the 2/3 is 25. And if you think about it, that makes sense, because 125 is 5 to the first times 5 to the first times 5 to the first. Well, 5 to the first is 1/3 of the way, and 5 to the first times 5 to the first is 2/3, and then 5, so this is 3/3. So we could look at this as, well, 125, right, factors down into 5 times 5 times 5. So 2/3 of 125 to the first is 25. I hope that makes sense to you. So negative 64 to the 2/3 power. Well, we have power divided by root, so it's the cube root of 64 squared. Oh, pardon me, it's negative 64, isn't it? Well, we can take the cube root of a negative number. That's not a problem. So cube root of negative 64, and then square it. Well, the cube root of 64 is 4, so we end up with negative 4 squared, or 16. Negative 36 to the 3/2, so power over root, so it's the square root of negative 36 cubed. So we can cube negative 36, and then take the square root, or we can try and take the square root of negative 36 and then cube it. Well, either way, if we cube negative 36, we're going to get a negative result, and we're going to try and square root that negative. Or we can try and square root that negative right away, and we can't do that, and then cube it. So this one is going to be no real solution. There's no real number there. 81 to the negative 3/4. Now this is not a negative number. Remember, this is a negative exponent. So we're looking at power over root, power over root. So this will be the 4th root of 81 all raised to the negative 3 power. Well, the 4th root of 81 is 3. So we get 3 to the negative 3rd. And if we remember our laws of exponents, this is the equivalent of 1 over 3 cubed, right? A negative exponent in the numerator becomes positive in the denominator, and 3 cubed is 27. So our final answer here, 1 over 27. And I will save 8 to the negative 1/3 for you. You can bring that to class. Here's some more samples. 19 to the 1/2 power. Here we want to write each exponential as a radical. So power over root, this is simply the square root of 19. B and C, we'll look at these in conjunction with each other. We have 14 x to the 2/3. In this case, the 2/3, power over root, is only on the x. So this is 14 times the cube root of x squared. Versus C, now we're taking the 2/3 of the 14 as well. 14 and x, it's power over root. So it's the cube root of 14x quantity squared, or the cube root of 196 x squared, because we have to square the 14 and we have to square the x. X to the negative 5/7. This is a little more challenging. Again, this is not going to be a negative result, but we do have a negative exponent. So we have power over root. So that is the 7th root of x to the negative 5th. Now we're not quite done here. This is the 7th root of 1 over x to the 5th power. And in E, x squared plus y squared raised to the 1/2 is the square root of x squared plus y squared. And just for clarification, this does not equal the square root of x squared plus the square root of y squared. That is an invalid operation. We would have to simplify this first and then take the square root. Try putting in something like 3 for x and 4 for y and see if you get the same answer, and you'll see that you don't. So bring that to class, let x equal 3, let y equal 4, and show me why these two are not equivalent. Let's write each radical as an exponential. Well, we have the square root of 37. We know it's power over root, so that's just 37 to the 1st power. So 37 to the 1/2. The 4th root of 9 to the 8th, I don't want to figure out what 9 to the 8th is, but I know this is power over root, so it's 9 to the 8/4, right? Power, I have the 8th power, the 4th root, which is 9. 8 over 4 is 2 over 1, so that's 81. And the cube root of negative 8, that's negative 8 to the 1/3 power. Here are the rules for rational exponents. This will look a lot like your rules for the laws of exponents. The first one here, a to the x times a to the y. We have the same base a. Power times a power. We simply add the exponents, a to the x plus y. A to the x divided by a to the y. Now again, we have the same base a. So we have a power divided by a power. So we subtract the exponent in the denominator from the exponent in the numerator. So a to the x minus y. Which leads us to this one right below it. If y, the absolute value of y is greater, or if y is greater than x, then we end up with a negative exponent. So a to the negative y is 1 over a to the y. Which is the same as 1 over a all raised to the y power. And that also leads us to, well, not quite. Let's go to a power raised to a power. So here we have base a to the x all raised to the y. So we have power raised to a power, so we multiply our exponents. In this rule we have two different bases, a and b, a times b, that whole quantity raised to the x. Now here we can impose the x on both. We can do that when we have multiplication and division. Remember, we cannot do this for addition or subtraction. A plus b to the x does not equal a to the x plus b to the x. Do not do that. But because we have multiplication and division, that does work. So a to the x times b to the x, or a to the x divided by b to the x. Now here, in our final example, we've got different bases, a over b raised to the negative x power, which is the same as b over a raised to the positive x power. So we can just flip our fraction and we end up with a positive exponent, which of course is b to the x over a to the x. You might see this using our previous rules. That's a to the negative x over b to the negative x. So we know a negative exponent in the numerator becomes positive in the denominator. So a to the x in the denominator, and a negative exponent in the denominator becomes positive in the numerator. Now remember, a negative exponent is not a negative number. It's a reciprocal. A negative exponent is a reciprocal. A negative exponent is a reciprocal. You may want to write that in your notes. So that's how we get b to the x over a to the x, which is the same as b over a to the x. So these are all equivalent here. So our final sample problems, let's write these with only positive exponents. 3 to the 1/2 times 3 to the 1/3. I have the same base 3. So I have a power times a power. I add the exponents. So that's 3 to the 1/2 plus 1/3. Well, if I want to add these two fractions, I need a common denominator. So that becomes, our common denominator is 6. So 3 to the 3/6 plus 2/6 is 3 to the 5/6. 7 to the 2/3 divided by 7 to the 4/3. So that's 7 to the 2/3 minus 4/3, which is 7 to the negative 2/3. Well, those aren't positive exponents, so that becomes 1 over 7 to the 2/3. So that's our final answer for B. For C, there's a couple different ways to do this. We have x to the 3rd over x to the negative 2nd. We could simplify this and try and simplify this and then impose the half, since this is all multiplication. Okay, we could do a power raised to a power and multiply these and then simplify. So there's a couple different ways. to approach this one. I think I'm going to pose the negative 1/2 first and then put it in positive exponents. So I get x to the negative 3/2 times y to the second, because negative 4 times negative 1/2, all over, well, x to the negative 2 raised to the negative 1/2, that becomes x to the first times y to the negative 1/2, and negative 1 times negative 1/5 is negative 1/10. So let's simplify these separately. So I've got a power divided by a power, same base x here, so I'm going to subtract x to the negative 3/2 minus 2/2, which is x to the negative 5/2, and that's in the numerator, times, also in my numerator, I'm going to subtract the negative 1/10 from 2, so that's y to the, that's really 20/10 minus, well, it's going to be plus 1/10, because I'm going to bring that negative 1/10 up, so it becomes a positive 1/10 in the numerator. So my denominator is now 1 for the moment, x to the negative 5/2 times y to the 21/10, and so I have y to the 21/10 in the numerator, all over x to the 5/2 in the denominator. That was a little bit of work. That might be tough to follow. We may have to review that one in class. And finally, problem D, we have r to the 3/5 plus r to the 8/5. These are different exponents. The temptation here might be to try and add these two, but we have a power plus a power. We can't do anything to the exponents, right? This is no different than, for example, having r cubed plus r to the 8th. We wouldn't make that r to the 11th because they're not like terms. We're not going to add those. We can't add the exponents. So same thing here. So all we're going to do is distribute, which something interesting happens. We have r to the 2/5 times r to the 3/5 plus r to the 2/5 times r to the 8/5. Now I have a power times a power. I can just add my exponents, and I will leave that for you to finish off and bring that to class as well. So that wraps up our introduction to rational exponents. Lots of sample problems there. We'll see you in class.